Alright, next lesson is semantic analysis. We're moving on to the new semantic analysis section. So let's go. Semantic analysis. At this point we have talked about lexing and parsing. Lexical analysis has converted an input stream of characters into tokens. Syntactical analysis has converted the stream of tokens into an AST. Next phase of the compiler is semantic analysis, which checks that the AST represents a valid, well-formed program. Each of the first three stages may detect some kind of error in the program. Lexical analysis detects lexical errors, ill-formed tokens. Syntactic analysis detects syntax errors, and semantic analysis detects semantic errors, such as static type errors, undefined variables, and uninitialized variables. Once semantic analysis is complete and successful, the program must be a legal program in the programming language. No further errors in the program should be reported by the compiler. Cool, so this is the last error reporting step. In addition to checking that the AST is a valid program, semantic analysis may also compute additional information that is useful for the rest of the compilation process. For example, the types of expressions. The types of each, the resulting type of an expression. The memory layout of data structures. Or non-AST representations of classes and modules. Okay. The output of successful semantic analysis is thus a decorated AST in which the AST has been augmented with additional information. Type checking. For many languages, static type checking is the core task of semantic analysis. It is conventionally implemented as a recursive traversal of the AST. To see how this works, consider the problem of type checking uses of the operator plus, since it shares many new features with other binary operators. In an object-oriented language like Java, it is natural to define a class that captures the common features of all binary operators, such as the left and right operands. Binary expression, extends expression, you have the left and right parts of the expression. Let us suppose that our type checker is intended to record the type of each expression node in the AST. This decoration can be expressed by adding an instance variable to the common superclass expression. Optional type is empty before type checking. Abstract expression type check throws semantic error. Okay. The variable type is a decoration to be filled in by semantic analysis with an actual type. The method type check is used to implement type checking, with each node class supplying the logic for type checking the kind of expression it describes. It is natural for type check to be a recursive method. Note that no arguments are given for type check. We see shortly that at least one argument is needed. Okay. Now let's try to write code for type checking addition in Java. Here's a simplified version of that code with some missing pieces. Assuming we have an existing representation of the types indent string, we might write code like the following, using recursive method calls to type check the subtrees left and right. Plus extends a binary expression. Okay, so the type check function checks the left hand side, checks the right hand side. If the left hand side is an int and the right hand side is an int, we set the type so type comes from expression. We set the type to the int type. If the left hand side equals string type, it doesn't matter what the right hand side equals because we want to implicitly convert to string. Makes sense? If it's none of those, we throw an error. Cool. Typing contexts. That something is still missing can be seen if we consider how to type check an identifier expression, such as a local variable. The body of the type check method is impossible to implement because we have no way to know what type identifier name should be associated with. So an ID extends an expression, the name, type check, right, so we don't know the type. In general, when doing semantic analysis of some part of the program, we need a description of the surrounding context in which that program fragment is located. When doing semantic analysis of some part of the program, we need a description of the surrounding context in which that program fragment is located. To handle type checking identifiers, the context needs to include an environment that maps identifier names to types. In the setting of compilers, this environment is known as a symbol table, right, circling around. A simple typing context might look like the following. So for the context class, we have a type, get the name, we give it a name and we get a type. Cool. And obviously if there's not a matching name, then we have an error. Then we modify the signature of type check to take a context as an argument. The implementation of id.typecheck becomes easy. So back in the class ID, we type check, give it a context, return c.getName. Cool. Cool. So it's just like a handle for getting the type based on an ID. However, the change to the signature of type check means that the context must be threaded through all recursive calls. For example, the method plus.typecheck is updated accordingly. So typecheck for typecheck for the class plus, pass down the context. Make sense? Formalizing typing context. We represent environments more formally as a mapping gamma from identifiers X to type T. What? Say that again. We represent environments more formally as a mapping gamma from identifiers X to types T. Okay, that makes sense. An environment gamma is written as gamma equals x1. So this is sort of like key values, I guess. The key x gives a value, x1 gives value t1, key x2 gives value t2, etc. Meaning that each identifier x sub I is mapped to the corresponding type t sub I. Also, I'm not sure if that's how you pronounce that, t sub I, x sub I. I'm not sure if that's what that means. Could be embarrassing myself. I'm going to look that up. I don't think I can copy this, man. One sec. I'm going to double check with ChatGPT. Yeah, t sub 1, t sub 2. Cool. Using this notation, let's consider the following example. Assuming that the initial typing context has no variables in scope. Okay, so our context is an empty set. Now we give it the identifier, the identifier I, and the identifier N. We now have this key value pair, this key value pair. Makes sense. Nothing changes here. Nothing's initialized. Sorry, nothing's declared. Now we have a new declaration here. So our gamma includes this key value pair, and then once we leave the scope, what was it saying about scope? Assuming this one has no variables in scope. Yeah. Once we leave the scope, we lose this key value pair, and once we leave all the scopes, we return to having the empty set. That makes sense. As we can see, the typing context changes as we encounter variables, declarations, and at the exit two scopes. For example, we might implement type checking for variable declarations as follows, adding the declared variable to the context. So the declaration extends the statement node. We have a name and a type on the declaration. Type check. Right, so declaration class, its type check literally just adds to the context. Makes sense. This implementation is designed under the assumption that the statements in a given block are checked sequentially, allowing new declarations to be accumulated by simply mutating the current environment. So a block extends a statement, we have a list of statements, type check, push the context, oh wait, what? What's happening here? What are we pushing? What are we pushing to C? And what are we popping from C? For all the statements, S, type check C, right, okay. So we're pushing nothing here. Then we're, I'm confused. However, the example above shows blocks introduce another challenge. Variables must go out of scope. One way to implement this is shown in block. The context maintains a stack of environments, right? So that c.push saves the current environment, and c.pop restores the most recently saved environment that hasn't been restored. Okay, but alright, so you're pushing something, you're pushing C, oh wait, we're given the class, where's context? I guess they didn't define the push function. That's alright, so the push function saves current environment, and the pop function restores the most recently saved environment from the stack of the stack of contexts. Implementing typing contexts. Programming languages tend to have a lot of mechanisms for introducing new scopes. For example, in Java we have blocks, methods, classes, including nested classes, and packages. The typing context needs to be able to keep track of what identifiers are bound in all these scopes. Stack of hash tables. The traditional implementation is as symbol table. The traditional implementation is a symbol table implemented as a stack of hash tables. That makes sense. So the stack is the environment stack, and the hash tables are the context, which includes key value pairs of identifiers and types. The symbol table is updated imperatively during type checking. On entry to a new scope, a new empty hash table is pushed onto the stack, taking constant time. On exit from a scope, the top hash table is popped from the stack, taking constant time. Adding a new identifier to the context just requires adding a mapping to the top hash table in constant time. However, looking up an identifier requires, in general, walking through the stack, checking each hash table for an identifier at depth D. This takes linear time. Of course, the value of D is small in most programs. Immutable search tree. A second way to implement the typing context is to use a persistent, non-destructive data structure such as a binary search tree. A binary search tree can be updated in log n time to produce a new binary search tree without affecting the original. Just going to see what this link is. Huh? Why did that link to OCaml? Weird. It's not even like a data structure thing. Like algorithms and data structures. Whatever. Anyway, binary search tree can be updated in log n time to produce a new binary search tree without affecting the original. This is possible because the data structure is immutable and the new binary search tree shares all but big O of log n nodes with the original tree. On entry to a scope, no change is necessary. As bindings are added to the environment, new contexts are constructed. On exit from a scope, extended context is simply discarded. One advantage of this implementation is that the context used to check a given expression can be saved as a decoration since it is immutable. Okay? And the third type for implementing typing context is a hash table with duplicate entries and a log. If a mutable implementation is acceptable, the asymptotically optimal data structure is a single chained hash table in which we allow duplicate keys to appear in the same bucket. In addition, the context keeps track of a log of updated keys, which can be implemented as a linked list. A log of updated keys. Okay. An identifier is looked up by using the hash table directly and taking the earliest matching mapping in its bucket, taking constant time. There may be other mappings, but the ones belonging to outer scopes will be later in the bucket list. Okay. An identifier is added to the data structure by inserting it at the head of its bucket list and also recording it at the head of the log, taking constant time. On entry to a new scope, a special marker is put at the head of the log, a constant time operation. On exit from a scope, all identifiers are popped from the log up to including the first marker. Okay, makes sense. Each such identifier is removed from the hash table in the usual way as well. Each such identifier is removed from the hash table in the usual way as well. The local time to do this operation is proportional to the number of variables in the innermost scope, but that number is also proportional to the number of put operations, so the total time to enter, add variables, and exit scope is still proportional to the number of variables added. Yeah, that makes sense. Hence, the amortized complexity of exiting is also big O of 1. This implementation is probably the fastest, but is not so easily constructed using off-the-shelf data structures. Okay. Yes, the trade-off being here is the trade-off between the top one and the bottom one is more complexity and more space, less space efficient, but overall more efficient. Cool. What's next? Type systems. Cool. Strong for static typing. Some common type constructions. Constructors, that is. Oh, cool. Records. Actually was using records at work the other day, but I am not 100% sure what they are, but definitely going to look this up more. Array types, reference types. Cool. Alright. I guess I'll make another video for that later. Thanks for watching.